In Lesson 9.4, Polar Coordinates and Polar Graphs, we're going to begin our short study of the polar coordinate system. The title of this lesson is a little bit of a misnomer because we will start to get into the calculus of the polar system towards the end of this lesson. Anyhow, the polar coordinate system differs from our standard XY rectangular coordinate system in a couple key ways. First off, the XY coordinate system works by simply telling us how far to go from the origin on the horizontal and then how far to go on the vertical. So it's essentially a two coordinate system, which leads us to a point. And of course, we can make graphs based on a whole set of points that satisfy some equation that all tell us the x and y coordinates. Well, the polar coordinate system is different because in the polar system, all points are derived from looking at the distance of the point from the center, which we're going to call the pole, and then looking at what angle that we have to go from the pole to get to that point. So think about this. In the rectangular system, we need x and y. We need to know how far sideways, how far up and down. In the polar coordinate system, we need r, which is how far from the pole we go, and we also need theta, which is what angle we go from the using the standard, if you recall the unit circle from pre-calculus, that standard system where we start with 0 degrees being the positive x-axis, and we'll go around back to 360 degrees or 2 pi, which is what we'll actually be dealing with here. The polar coordinate system is very, very useful when the distance from the pole to the point you're looking at is more important than simply the coordinates of the point itself. I'll bring up tactical situations that are often used in warfare, definitely dealing with submarines or any kind of trajectories. You want to know how far you're going to be shooting, not necessarily the horizontal and the vertical, but rather how far and in which direction. You can see that for that reason, vectors do play a big part in the polar coordinate system, but that'll come when you get to Calculus 3. So, we're going to begin our study of the relationship between the rectangular and polar coordinate systems by looking at some very, very important conversions that we can do between the two. So, let's go ahead and start by looking at how to get from one coordinate system to the other. So actually, before we get into looking at the conversions between the rectangular and polar coordinates, let me first introduce you to the way that each of these graphs look and some of their commonalities and differences. First off, you see here the rectangular coordinate system, and the rectangular coordinate system is something that is tried and true. We've been familiar with this for ages and ages, and it's what we're most familiar with, really. In the rectangular coordinate system, we're always given a point in an x comma y sort of fashion. Now this is something that a lot of beginning Algebra 1 students often make errors on. Is it x comma y? Is it y comma x? How do I find the points? Where are they? We know now, of course, that it is x comma y. And the x is going to represent the horizontal and the y will represent the vertical. What I mean by that is if I have a point, and let me make this up. Let me have a point such as 2 comma negative 1. This tells me that I'm going to go over 2 on the x, and all of the points on this red line, all of the points on the red line are going to correspond to points where the x value is 2. Alright, and so what I can do is I'm going to go ahead and say that is where the x value is 2. The y value we need to be negative 1. And so this blue line right here corresponds to all of the points where the y value is negative 1. And now that brings us to the question, are there any points where the x value is 2, in other words, it's on the red line here, but also the y value is negative 1, so it lies on the blue line? And clearly, of course, there is such a point, and it is going to be the point right there where those two indices pretty much meet or cross, intersect, however you want to call it. Alright, that's the rectangular system. Now let's take a look at the polar system. You can see that the polar graph kind of looks like a radar of sorts, and in fact, polar graphs are used for radar positioning and things of that nature. In a polar system, instead of using x comma y coordinates, we're going to use what we call r comma theta coordinates. Now, the r coordinate essentially tells us how far out we're going from the origin, which I'm not going to call the origin anymore, and you shouldn't either. The reason it's called a polar curve is because the origin, what we used to call the origin, we are now going to call the pole. So it has nothing to do with temperature or weather. It's not polar like that. It's polar because it's based on the pole. And the pole you can think of as like a North Pole or South Pole, just this thing sticking out. And it's kind of what everything is referenced around. There's the pole. Here the pole is at the origin. So, if we do want to plot a point in the r comma theta sense, let's just go ahead and plot, just for fun, let's say 1 comma pi over 3. 1 comma pi over 3. So the 1 for r tells us that the point we're looking for is going to be located somewhere on the unit circle. That is, it's going to be 1 unit away from the pole. Of course, if r were 2, it would be on the second unit circle, or the third unit, fourth unit circle, so on and so on. So r always represents a circle that is a uniform distance from the pole. Now, the pi over 3 part of this tells us at which angle we're going to have to go to find our point. Now, remember that this is always going to be 0 right here, whether it's degrees or radians. This is 0. This is always going to be pi over 2. This is pi. This is 3 pi over 2. And then we come back to this could also be 2 pi. So, it's just like your unit circle from pre-calculus or trigonometry. Same thing. So, where is pi over 3? Pi over 3 is going to be this right here. And I'm going to draw an arrow because this ray does go out infinitely for infinity, or whatever you want to call it. Alright, so is there a point on the first unit circle, in other words, where r equals 1, the first unit circle, where our theta, or angle, is pi over 3? And clearly there is such a space. Hopefully you can see that for yourself. It's actually going to be this point right here. Alright? That has an angle of pi over 3 from 0, from the positive x-axis, and it is 1 unit away. So, that's the polar coordinate system. Now, this isn't very common, but if I do put the two coordinate systems together, I get what I'm going to call the hybrid system, and you see that here. In our hybrid system, we can see that our point 2 comma negative 1 from our rectangular example shows up about right here. And we could find a polar coordinate for that. It looks like it's a little bit more than 2 units away from the pole. And I'm not quite sure what angle it's at, but it looks like just a little bit less than negative pi over 6. If I'm going from here, it's just a little bit less than pi over 6 to get there. Likewise, if I plotted the polar point that I did earlier, 1 comma pi over 3, that would be right here. And could I find the rectangular coordinates for that? I think you could argue that certainly we could. It looks like maybe it's 1/2 out on the x and just a little bit short than 1 out on the y. I'm not quite sure what the coordinates are, but it's that far out on the x and that far out on the y. So maybe I could do something to find that out. Maybe there's some formulas or some way that I can connect one to the other. Well, let's go ahead and see. I think we'll find here that the conversion between rectangular and polar coordinates really is not that difficult and involves no knowledge beyond basic right triangle trigonometry. Let me show you what I mean. If we begin by looking at a polar coordinate, let's say, and I'm just going to make this up, but let's say 3 comma pi over 6. That's going to put us right here, 3 comma pi over 6. And looking at that, you can kind of estimate what the x and y coordinates will be going to be here. It looks like for the x, we're going to go over about that much, somewhere between 1 and 2. And as far as the y goes, looks like we're going to rise somewhere between 2 and 3. So there's some kind of estimate. Of course, this would be our x, and this would be our y. And that would be our x and y value. However, that is information we don't have. That's the information we're trying to find. Really, all we were given here is our r, which is kind of like the hypotenuse of a right triangle, as well as our theta, which is how many radians we had to go through to get to this ray right here. So take a look at this right triangle. If we are given the r and we're given the theta, what do I need to do to find x and y? In other words, what I should say is, if we cover up this y right here, what relationship do the r, the theta, and the x all have to each other? And hopefully you can look at this and kind of see for yourself that really we're just talking about a cosine. In fact, what I could say here is that the cosine of theta is actually just equal to x over r. And actually, let me make that a blue r to match our picture. So cosine of theta equals x over r. Now, in this formula, if I wanted to solve for r, solve for x rather, I want to know what x is. How in the world can I solve for x? How can I get this equation to say x equals? And clearly all you really need to do here is just multiply by r on both sides, and we'll have r cosine of theta. And that is how we express x if we're given a polar point. So let me go ahead and write that over here. X is simply equal to r cosine theta. That's going to be very, very important, not just when translating points back and forth, but actual equations as well. So that worked out quite nicely. Take a look at this triangle and see if you can find a relationship between r, theta, and y. And hopefully you kind of see for yourself that there's a very similar relationship, except that this time it involves sine rather than cosine. So sine of theta is going to be y over r. That is the opposite over the adjacent, where the cosine was the adjacent over hypotenuse. Rather, sine is opposite over hypotenuse. Cosine adjacent over hypotenuse. So if we go from here, of course, I just want to solve for y. What I'm going to end up with is that y equals r times the sine of theta, and that is going to be our formula for y. So I'm going to go ahead and write that over here. Y equals r sine theta. And this makes a lot of sense. If you learned in trigonometry that cosine represents the x and sine represents the y, then this conversion makes perfect sense. If you're taking physics and you've dealt with normal vectors and things with that dealing with friction and gravity, again, cosine is the x, sine is the y. This makes all kinds of sense. But what if I'm given a point in rectangular coordinates? I'm given an x and y. How in the world can I find theta and r? Again, I'm going to look at the same triangle here, except this time I'm going to claim that it was x and y that were given to me. And how do I find r and theta? Well, hopefully you can look at this and see for yourself that theta, let's see, what's the relationship between theta and y and x? Oh, well, we could say that the tangent of theta is the opposite over the adjacent, or tangent of theta is y over x. And if I want to solve for theta, that shouldn't be too difficult then. Theta is simply going to be the arctangent of y over x. I'm going to write that as my theta equation. It's simply going to be the arctangent of y over x. What that really is saying is that tangent is opposite over adjacent, and we're just doing the inverse of tangent to get that. So that's not too bad. And for r, I'm not even going to have to write anything down. Look again at our triangle. Remember that it is, in fact, a right triangle. And what is the relationship between x and y and the r that we're trying to find? Of course, you can do a Pythagorean theorem type relationship. X squared plus y squared equals r squared. And therefore, r is actually going to be the square root of x squared plus y squared. So again, you can memorize these four conversion formulas if you like. There's absolutely nothing wrong with that. But I would highly suggest that if you understand where these four conversions come from, it sure makes it a lot easier to remember them in the future. So, all that being said, let's work on converting the coordinate system of a couple points and see how this whole thing works out. Before we proceed with these first two examples, wherein we're going to try to change the coordinate system in which each point is graphed, I am going to make aware to you that this entire process we're about to run through can be done on your graphing calculator. Now, if you have a computer algebra system on your graphing calculator, such as the TI-89 or the Inspire CAS, it may give you the exact answers. The 83, 84 will not give you exact answers, and for that reason, you should use that calculator function to check your results, but not to come up with your results. So just fair warning. Also, I'm not going to discuss that calculator function anymore. You can find it for yourself, learn how to use it, not a problem. But I'm going to show you how to do all this by hand. So, the first thing that I should tell you is that really we don't know whether this point here is in a rectangular or a polar form. So let me just go ahead and tell you that this is a polar graphed point, while this one is a rectangular. And we're going to try to convert it to the other. So this polar, we're going to try to take this to rectangular, while this rectangular we will try to take to polar. So just a point of information there, no big deal. So for our first example here, we have negative 2 comma 7 pi over 6 in polar form. I want you to take a moment and see if you can figure out where on the graph this point is going to go. Now, you might need to draw your own graph on your notes, but I actually do have one right over here, so I'm just going to go ahead and use that. Negative 2 comma 7 pi over 6. Okay, now the negative 2 does tell me that I'm going to be on the second unit circle. All right, so somewhere along this circle is where I'm going to be. In fact, if I go ahead, let me just highlight that circle. I draw circles very terribly, but there we go. Now, 7 pi over 6, you should be familiar with where that angle is, and that's going to be right there. Now, the question is, where does negative 2 as my r value and 7 pi over 6 as my theta value, where do they intersect? And I know your first thought is that they probably intersect right here. However, I'm going to caution you. That point that I just marked is actually positive 2 comma 7 pi over 6. The negative 2 tells me I actually need to head backwards, go in the other direction. So we're actually going to mark this right here as negative 2 comma 7 pi over 6. And in fact, I'll even write that here. Negative 2 comma 7 pi over 6 is actually going to be right here. So what is that in rectangular form? If you look very, very closely, the x value looks like it's a little bit under 2, and the y value, well, the y value looks like it's near about 1, but I don't know. Let's see how this works. Of course, I know that to find my x value, I'm of course going to go r cosine of theta, and if I do that, that's going to be negative 2 times the cosine of 7 pi over 6. So hopefully you're up on your unit circle knowledge. Cosine of 7 pi over 6 is, of course, negative radical 3 over 2. So there's my x value, and in fact, if I simplify this a little bit, I'm just going to get square root of 3. Interestingly, square root of 3 is just a little bit short of 2, which I can tell on my graph. So if we want to find our y value, y is going to be r sine of theta. And of course, if I just fill in the values I know now, that would be negative 2 times the sine of 7 pi over 6. Again, hopefully you are up on your unit circle knowledge. The sine of 7 pi over 6 is negative 1/2, which is going to give me a y value of 1. So, in rectangular form, it looks like that this point is going to be square root of 3 comma 1. And if I look back at my point, that actually does make a lot of sense. That does work out. So that's pretty sweet. Now let's go the other way. Now I'm given the point 3 comma 3 in rectangular coordinates, and that's going to graph to about right here. This is going to be 3 comma negative 3. And what I need to do now is convert that into r and theta, the polar coordinates. So r, if you look very carefully at r, 1, 2, 3, it's just a little bit beyond 4 units away from the pole, just a little more than 4 units. So that unfortunately is not going to suffice here. So let's use our formula. We know that r is essentially the hypotenuse of a right triangle. In fact, if you want to see that right triangle, here it is. Now, of course, I can only use that as a reference, but my x squared is going to be 3 squared. My y is going to be negative 3 squared. And you can do a little bit of simplifying of that on your own. You're going to get the square root of 18. Or if you really are adamant about reducing your radicals, this would give us 3 radical 2, which, if you multiply that out, is just a little bit more than 4. So that clearly does seem to apply to our r value here. Now, of course, theta, as we've already discussed, is the arctan of y over x, which in this case is going to be the arctan of, let's see, if I plug these in, that would be negative 3 over 3, which is actually just negative 1. So what is the arctangent of negative 1? That, of course, is negative pi over 4. So it looks like our point in polar coordinates is actually going to be 3 square root of 2. That's my distance to the pole. And then at the angle of negative pi over 4. And certainly that does work out visually on the graph. And everything here looks to be really good. So that's how we use these conversion formulas to convert a point in one coordinate system to a point in another coordinate system. Just be aware there is a third common coordinate system that's called cylindrical coordinates, although that actually plays off on the polar coordinates and extends it to 3 dimensions. You'll get used to that later on. But all this being said, let's see how to use these conversion formulas to convert equations from one coordinate system to another. This is going to be pretty fun and exciting. In our second example, we are going to convert equations from one form to another, and we're going to graph those equations just to see what they look like. Of course, we're more used to graphing in a rectangular system, so let's go ahead and begin by just graphing this equation right here, y squared equals 9x. Clearly, if x equals 0, you should see that y equals 0, meaning that we have a point at the origin. Let's just see what happens when x is 1. If x is 1, do math here, and you'll see that y could be positive 3 or negative 3. And when x is 2, we're going to have the positive and negative square root of 18 for y, which is not going to fit on our graph. But I will tell you that if we do this correctly, what we should end up with is a sideways parabola. And you should be familiar with that. That's one of the conics that we looked at not too long ago. So, how do we take this rectangular equation right here, which we know is rectangular because it has x's and y's, and how do we turn this into a polar equation with r and theta? Well, the amazing thing is we're going to use those same 4 conversion formulas that we used for points to convert equations. Check this out. Do you remember what y equaled? Hopefully you remember that y is just r sine of theta. So there's y, and of course that needs to be squared as per my rectangular equation. And then what was x? X, of course, was r cosine of theta. So there we go. Let me go ahead and square this just so we're working with a completely expanded out equation here. And on this side, I'll multiply the r cosine theta by the 9. All right, so all we need to do now is a little bit of algebra. We need to solve for r. We want an equation that says r equals something with theta in it. All right, so notice that I do have r squared over here, and I do have r over here. So what I'm going to do is divide both sides by r. And if I do that, of course, I should put a restriction that r cannot equal 0. Of course, if r did equal 0, I'd be in trouble with what I'm doing here. So I'll just toss that value out. And what I'll end up with is r sine squared of theta. And then over here, the r's will cancel out, and I'll just be left with 9 cosine of theta. So there's a couple different things that I can go to do from here. If I want to get r by itself, how can I express what r equals? Well, I could write 9 cosine of theta divided by sine squared of theta. That would be acceptable. That would be acceptable. I could write this as 9 cosine of theta times, what would this be? Cosecant squared of theta. That would be acceptable. Heck, if you wanted to, you could write it. One of those signs on the bottom could go with the cosine, and we could say this is 9 cotangent of theta, and then a cosecant of theta. There's a lot of ways you can write this, but I challenge you to attempt to graph any of these on your graphing calculator, and I bet you see the same sideways parabola that we have drawn right here. So that's pretty cool. We should make one quick restriction here. Remember, we did say that r cannot be 0. And that makes a lot of sense, because if r were 0, would theta be 0? Could theta be 0? Try it. Plug theta into this equation. Do it in your head. Plug 0 in for theta. Let's see here. If I go back to my original right here, sure, I would get 9 on top. Cosine of 0 is just 1, so I'd have 9 on top. But look, that you'd have a 0 on the bottom, and then everything just goes awkward. So we'll just say that r cannot be 0. Clearly, that implies that theta cannot be 0 as well. So there we go. So that was kind of interesting. Let me draw a little divider here to keep our work separate, because what we're going to do now is convert r equals 3 secant theta. All right, we're going to turn that polar equation into a rectangular equation and see what it looks like. R equals 3 secant theta. So what is r in the rectangular system? And if you go back, hopefully you recall that using the Pythagorean theorem, r was just x squared plus y squared square rooted. All right, so that works out. If I write this right here, let's see if I could write this as 3 over cosine theta. Would that make any sense? Well, I would need to put an r down here, and all of a sudden everything is wacky. I really need this to say 3 over r cosine theta. How can I get that to happen? Well, I could divide both sides by r from the get-go, and that would just give me a 1 on the left side. So that's one option I have. Of course, if I do that, divide both sides by r, that would give me this equation. 1 equals 3 over r cosine theta. And of course, r cosine theta is really just another way of saying x. So this would say 1 equals 3 over x. And then if I do a little bit of algebra here, I would get x equals 3. But that seems entirely too simple. And really, this would just graph as a straight vertical line? It just seems too simple. So let's go back and try this way, since it's fun to make a mess of things. 3 divided by cosine theta. We know what theta is. In fact, I don't even need to write it this way, doing it like this, because I can just say this is r, and then 3 secant. Do you remember what theta equals in the rectangular system? Remember that that's just an arctan of y over x. Alright, so I have this big radical equals 3 secant arctan y over x, all this mess. I do challenge you to draw a right triangle, draw the arctan of y over x, and find the secant of that angle. For the sake of time, I'm just going to go ahead and spill the beans on this one. But I certainly encourage you to try this on your own and see that what I'm about to show you does work. What we would actually end up with is 3 times x squared plus y squared on top. And we would actually just end up with x on the bottom. Now this is very interesting, because look where I'm going to go from here. I'm going to divide both sides by this ugly radical. And when I do that, I'll get 1 equals 3 over x. And that's exactly what I got when I did it the easy way. So you know what? I guess it works, and that's pretty sweet. So we're going to end up with x equals 3. Of course, we can graph that. That's going to be, as I said earlier, this vertical line right here. And again, take your graphing calculator and graph r equals 3 secant theta and see what happens. See if it actually is a vertical line. And it's pretty impressive. While you're at it, try some other polar equations. What happens when you do r equals 3 cosine theta? Or 3 sine theta? See what effect that has. That knowledge could be very valuable to you later on. But having done all this, let's take a look at another thing. What if we want to find the slope of a polar equation Of course, we want to find the slope in rectangular form since we're so familiar with delta y over delta x. So let me show you how to do that now. Now, so long as you remember our conversion formulas, that is, x equals r cosine theta and y equals r sine theta, so long as you remember those conversion formulas, I'm going to argue that finding the slope of a polar function is not incredibly difficult. It's an ugly formula. If I was to write this for you right now, you would not be happy. It's ugly. But consider this. Dy dx, the derivative of y divided by the derivative of x. We're going to do it exactly that way. We're going to find the derivative of y with respect to theta, and we'll divide that by the derivative of x with respect to theta. So essentially, it's going to look like this. We're going to find the derivative with respect to theta of y. Now remember that y is simply r sine theta. And we're going to divide that by the derivative with respect to theta of x. And remember that x is r cosine theta. If you remember this little fact, none of this is really that difficult. We will, of course, need the product rule because r and sine theta are two different functions, but this won't be incredibly difficult. Let's see, the derivative of r sine theta, we could call that r cosine theta if we differentiate the second part first. And then if we differentiate the first part first, we get r prime sine theta. Alright, so that is going to be the numerator of our slope. Is it ugly? It's ugly. But understand where it comes from, and it's really not that bad. On the bottom, we're going to do the derivative with respect to theta of r cosine theta. And if we do that, if I want to, I started with a regular r on top, so I'd prefer to start with the regular r on the bottom, although it doesn't really matter as far as the order goes. But if I keep this constant, the derivative of cosine is negative sine, and then I'll do r prime with the cosine. So there is your formula for the derivative of a polar graph. And if we run our r's and thetas through this, we'll actually get a derivative in the xy rectangular coordinate system. So that will be friendly to us. We'll still have our normal rise over run and all that good stuff. So if I want to formalize what I have written up there in the corner, let me go ahead and do it like this. The derivative of y with respect to x, when dealing with a polar equation of the form r equals f of theta, is actually going to say this. I'm going to replace all my r's with f of thetas as per this definition right here. And watch what's going to happen. I'll have f of theta cosine theta, and then I will have f prime of theta sine theta. Again, I'm going to tell you right now, I have never memorized this, although I probably should. But anytime I need to do it, I just differentiate the y on top, differentiate the x on bottom. So the bottom, the numerator, is going to say negative f of theta sine theta, and then I will have plus f prime of theta cosine theta. It is ugly, it is hideous, but remember where it comes from, and it's really not too bad. And now that you have it, let's see how to use it to find a few slopes on a polar graph. Alright, so here's a problem where they want us to graph this polar equation, which you can see I've done for you. It kind of makes kind of a cross between a heart and a butt, I guess, that kind of shape. But we want to find the slopes of the tangent lines to this graph at 3 of the points that they give us here. And let's take a look at those 3 points. 2, 0. Remember that 2, 0 is going to be right here. And again, this is not 2, 0 in rectangular coordinates. This is 2, 0 in polar coordinates. That means I'm going 2 away from the pole and then 0 degrees out. So that's going to be right there. 3, 7 pi over 6. So if I go, here's my 7 pi over 6. If I go out to 3, that's this right here. And finally 4, 3 pi over 2. So if I go out 4 units from the pole and go at an angle of 3 pi over 2, that's going to put me down here. So it's hard for me to tell exactly what the slopes are going to be, although I can certainly surmise a hypothesis on each one of these. I'm going to hold my hypothesis, and let's actually do some math and see what the actual results are. So, first thing I need to do is come up with my derivative. So dy dx, from before, I'm just going to go ahead and rewrite this. I'll have r cosine theta plus r prime sine theta, and that will be my numerator. I just need to figure out what r prime is. I already know r, of course. That was given in the problem. There's r. And then in the denominator, I'm going to have negative r sine theta plus r prime cosine theta. So this is actually all ready to set up, except that I don't know what r prime is. So let me just really quick go ahead over here and define r prime. You can do this however you like. If you want to distribute the two and then differentiate, if you want to do a product rule, however you want to do it. I do get that r prime is actually going to be negative 2 cosine theta. So that's what I'm going to substitute into these r primes right here. So let's go ahead and see how this looks. My r is going to be 2 times the quantity 1 minus sine theta. So there's r, and then cosine theta. That covers my first term, this term right here. All right. As for this term, that's going to say plus r prime, which is minus 2 cosine theta, and then sine theta. So that covers my second term, and there is my entire numerator. Is it ugly? It's ugly. But that's not always a bad thing. We'll see if it simplifies, and we'll keep going with it. Now, in the denominator, we're going to have negative r, so that will be a negative 2 quantity 1 minus sine theta. And this time we're going to multiply it by sine theta. And then over here we'll do r prime cosine theta. So here's my r prime, and with cosine theta. And of course I'm going to combine those together as a squared thing. So at this point, I'll simplify just a little bit, just really minor here. I notice that there are 2's all over this thing, so I'm going to go ahead and cancel out all the 2's. The 2's really aren't necessary here. Alright, and at this stage, I'm going to encourage you to pause the video and simplify this yourself. See what you come up with. And when you're ready, go ahead, unpause, come on back, and let's see if we get the same thing. So, hopefully you've given it a shot now. When I simplified this, and this is fairly ugly, but in the numerator, I was able to factor out a cosine theta, and when I did, I was left with 1 minus 2 sine theta. That's what I ended up with in the numerator. It's still ugly, but it's a lot better looking than it was before. In the denominator, I can write this a couple different ways. You probably have sine squared theta minus sine theta, and then plus, or that's minus cosine squared. This is probably what you have, and that's perfectly fine. However, it can be simplified just a little bit further, and I don't even know really if it's a simplification, but if we want to write it in terms of all signs, we can do that. So again, my numerator will stay the same here. I'm going to change my denominator. If I call this term right here, this cosine squared term, if I call that 1 minus sine squared, then I end up with an actually pretty nice simplification here, where my denominator will be 2 sine squared theta minus sine theta, and then minus 1. So personally, I think this is a lot prettier, although it's completely up to you. The previous answer is still correct. Alright, the great thing about this, this is the derivative dy over dx. However, notice that it is all in terms of theta. I don't even need to worry about my r. And that makes perfect sense, because this is a polar function. For each value of theta, there's only one r value. So it makes sense, similar to how when you do the derivative of y as a function of x, everything is in terms of x. Same thing here, everything is in terms of theta. So let's go ahead and work these out here. For my point 2, 0, which again is this point right here, I'll allow you to do the math on this. Remember, all you really need to do is not even worry about the 2. R doesn't even come into play. But plug in 0 for all of these thetas. I'll give you a second to do that. It's a lot of simplification and a lot of that stuff. But when you're ready, the result I get, I'm about to put here, is in fact negative 1. And that's very interesting because if you look at my graph, sure, the slope of this tangent line does appear to be about -1. And now mathematically I can say that it absolutely is. So let's go ahead and take a look at our second point. That is 3 comma 7 pi over 6. Again, a little bit of math here, and I'll give you a chance to do that. You have to plug 7 pi over 6 in for everything, and it's pretty hideous. However, when you do this, and if you do this correctly, what you're actually going to end up with is -3 square root of 3 over 2 all over 0. This is actually an undefined slope. And that, certainly, you can tell, it's a straight up and down vertical. So there you go, undefined slope. And now let's do one more. If we do the point 4 comma 3 pi over 2. Again, just plug the 3 pi over 2 in, and what you should end up with here is 0 over 2. And that means that at this point here, we do have a horizontal tangent. It has a slope of 0. So that's how you do all this. We're going to look at one more thing before we conclude these notes. We do need to look at how to find the derivative of a polar graph at the pole. When I say at the pole, in the case of this graph, I'm talking about this point right here, the point where the graph actually hits the pole. There's some special things that go on there. So let's go ahead and take a look at that now. So the last thing we need to discuss in the notes for this chapter is a special kind of tangent line. And what that is a tangent line at the pole of a polar function. Now there's a couple things I need to let you know about the derivative of a tangent line at the pole. The first thing I need to tell you is that that point is only going to exist. In other words, the line theta equals alpha is only going to exist at the pole if f of alpha itself equals 0. In other words, in order to have a tangent line at the pole, the function actually needs to exist at the pole. It's similar to in rectangular coordinates. If you're trying to find the slope of the tangent line at the origin, but the function doesn't go through the origin. How in the world are you going to do that? So that's our first condition. The function must actually evaluate to 0 at that value of theta. Secondly, and this is more of an interesting one, the derivative of the function at that value of alpha cannot equal 0. And this is a tricky one. If the derivative here does equal 0, then our tangent line is actually going to go like this. Again, it exists at the pole, and if the slope is 0, then the slope is going to look like this. Now, of course, the challenge here is, can you draw a polar function that passes through the pole and has a 0 derivative at the pole? Now, some of you might say, oh, well, we can look at a cardioid, which is something that would graph something similar to this. It's a sideways butt, if you like, or a kidney or something like that. The problem here, yes, this function does exist at the pole, but the slope can't possibly be 0 there. It can't be possible, simply because there would be a cusp here at the pole. How else could it look? Maybe you're thinking it would be a happy cardioid. In other words, one that goes like this. Okay, here, this function does exist at the pole, but would you say that the tangent line would look like this? I wouldn't. That would also imply that it's smooth when we know that there's a cusp right there. So the important fact of the matter is here, a tangent line at the pole will only exist if the function exists at the pole. That is our first condition. This says the function exists at the pole. That is, if theta equals 0, then r equals 0, or however you want to look at that. And furthermore, we can only have a tangent line at the pole if the slope at that theta value is not 0. So be very careful with that. Let's look at one example, and that will conclude our notes for this chapter. Now, in this last example of this chapter's notes, we're going to try to find the slope of the tangent line to the graph you see here at the pole. Now, we need to be very careful. Don't assume that the pole is always when theta equals 0. We really should solve and make sure. Now, of course, the one thing we do know about the pole is that at the pole, r equals 0. If r were anything other than 0, then those points would exist some units away from the pole. Remember, that's what r represents, the distance from the pole. So if r equals 0, there we go. Here is the equation of the graph that you see here. This is called a cardioid, of course. And so if r equals 0, then what I'm going to end up with this equation is 0 equals 3 times the quantity 1 minus cosine theta. Now, if you do a little math here, clearly divide by 3, we need to find a place where cosine theta actually equals 1. So, where does cosine theta equal 1? And in this situation, that does occur at 0. So we're safe here. But I just want to warn you, be very careful. If this were a sideways cardioid or something along those lines, or if it had a loop in it, it's possible that we could get a graph that looks something like this. This is a common kind of graph that we'll actually see in our next lesson. But in this case, if theta were equal to 0, we would probably be all the way out here and not at the pole. So be very careful. Here would be theta equals pi over 2, and we'd have some garbage going on in here. So I'm just warning you to be very careful. Even if it is a cardioid, that doesn't necessarily mean that anything's going to happen, or rather that the pole is where theta equals 0. In fact, if I look at this cardioid, where theta equals 0 would be this point right here. I would argue that we'd hit the pole when theta equals pi over 2. This would be when theta equals pi. This would be theta equals 3 pi over 2, and then back to 2 pi. So I'm just warning you to be very careful. However, in this graph, we are at the pole when theta equals 0, so we're good to go. What we're going to need to do is find the derivative of this function. Now that we know that theta equals 0 is what we're going to be using, let's find the derivative here. Dy dx is, of course, going to be r times the, we're going to do r cosine theta, and then we're going to have to add the derivative of r sine theta. So the derivative of r in this case is going to be 3 sine theta, and we'll tack another sine theta onto that. So that's going to be the numerator of my derivative. The denominator of my derivative is going to be r times the sine of theta. So let's see, that's 1 minus cosine. That's going to be times sine of theta, and then we're going to do r prime with a cosine of theta. Now, you're not going to have to watch me go through all the algebra and all the simplification. I'm going to give you the opportunity to do that. However, I am going to write down what the final simplified derivative is. So pause this video right now if you want to try it on your own. But if you're good or you have already tried it, here is the simplified version of this derivative. And of course, it can be messed around with. This cosine squared could be turned into sine squareds, or this sine squared could be turned into cosine squareds. But I'm just going to leave it like this. There's my denominator, and my numerator is actually going to be 6 cosine theta sine theta minus 3 sine theta. So again, I could pull out a 3 sine theta out of the bottom. I could cancel out all these 3's, but this will work good enough as anything. So what I want to do is let's go ahead and evaluate this derivative at theta equals 0. And again, I'll give you a moment to work that out. Of course, the cosine of 0 is 1, so there's going to be 3 times 1. This will be another 3 times 1, and this will be 3 times 0. So there's going to be my numerator. Down below, if I plug 0 in for theta, this entire term goes away because of the sine. This goes away because of the sine. And notice that I do end up with an undefined term. You can call it indeterminate if you want, but remember, we're not finding limits here. Don't L'Hopital this. We're not looking for limits. We're looking for the slope of a tangent line. So what have we found? Well, we found that although the graph did exist at the pole, and although theta equals 0 where the graph hits the pole, there is no tangent line at this point, and that makes perfect sense. As you'll notice, there is a cusp there. So, we've covered a lot in this lesson. This is only our introduction to polar coordinates. We're going to spend next lesson dealing with these as well, relative to area and stuff like that. The most important thing, obviously, are those four conversion formulas, but hopefully you're not going to memorize those. Hopefully you actually understand where those come from, because that makes everything a lot easier. Remember that the slope, or the derivative, of a polar graph is simply the derivative of the x part relative to theta divided by the derivative of the y part relative to theta divided by the derivative of the x part relative to theta. So it still is dy over dx. It just happens to be dy d theta over dx d theta. So as long as you remember your conversion formulas, it all works out quite beautifully. So with that, good luck on your 9-4 assignment, and don't forget that you can use your calculator on a lot of these questions. Good luck.